Okay, so since it's 2 minutes to 3 p.m., I'll just wait for a few more minutes and then we'll get started with the week 11 to session on constraint and unconstrained optimization. Okay, so it's 3 p.m. already, so though anyone hasn't joined yet, I'll get started with today's content. So this is the week 11 TA discussion. So the topics that I'll cover here will include week 11 assignment solution. Then I'll be talking about similar problems that you will find in week 12 assignment. So this will include the topics like barrier methods, barrier function methods. Then we will have dynamic programming, and finally we'll have multi-objective nonlinear optimization, or I'll just put it as multi-objective optimization. Okay, so without further delay, I'll get started with today's first topic, which is the week 11 assignment solution. The content will be very less. Actually, solving these 10 problems and discussing the week 12 assignment won't take much time. So I can probably wrap it up in 1 hour. So the rest 1 hour I'll just wait so that to see if anyone has any doubts. I know people posted queries in the discussion forum, but those are more of a side that same options were given, like two options being the same, those kind of confusions. I am not responsible to set these questions and those options. So only the course instructors or the main team of the course can resolve those issues. So yeah, keep raising those issues in the discussion forum. Hope they will notice and resolve it as at the earliest. Okay, so the first problem, I'll write down the problem and then I'll also write down the options and the solution. Okay, so the first problem tells you which of the following is or are true about Kelly's cutting plane method. So I think you have already gone through the Kelly's cutting plane method from the course lectures, and I think this is very straightforward question, but anyway, I'll just write down and give you the answer. So about Kelly's cutting plane method. Okay, so the options are the nonlinear objective function, objective function fx is linearized with Taylor series expansion. Expansion. Okay. The next option is the nonlinear constraints. The nonlinear constraints GIX are linearized. Okay. I think I need to mute this, but with Taylor series expansion. Option C is both of A and B cannot be true. And option D is none of this. Okay, so for this problem, as you can notice, in the Kelly's cutting plane method, what happens is that suppose you are given some nonlinear objective function fx and nonlinear constraints gix, then what you have to do, you have to use Taylor series expansion to linearize both of them, both the objective and the constraints. So option C and D are false here, and both option A and B are the correct answers. So I think I need not explain it much because this is directly from the lecture. So A and B are the correct answers. Next is the second problem. So that's a bit of interesting, I think, because that's, I think, not too theoretical, but has some numerical component into it as well. So the second problem tells you to maximize a function. So maximize f equals x square plus y square minus 6x minus 8y plus 10, and subjected to g1, which is the first constraint, which is 4x squared plus y squared minus 16 less than equals 0. G2 is 3x plus 5y minus 15 less than equals 0, xy greater than equals 0. So obtain Kelly's cutting planes for the above problem at point that is given. Okay, so I'll write it down. Obtain Kelly's cutting planes. So you have two constraints, right? So you need to have, I think, you will get two cutting planes corresponding to these constraints for the above problem at point x1 y1 equals 1 1. Okay, so the options, I'll write it down. first one is G1 approximated as, so this is, you can notice the first one is the nonlinear function. So that has to be linearized. And the second one is a linear function. So that will remain as it is, I think. So let's see how the options are given. So this is the first one. This then equals 0. G2 is the one that is given, right? G1 approximated to 6 plus 2y minus 16 less than equals 0. And G2 is 3x plus 5y minus 15 less than equals 0. Option C is G1 approximated as 8x plus 2y minus 21 less than equals 0, and G2 equals 3x plus 5y minus 15 less than equals 0. And option D is G1 approximated as 8x plus 2y minus 16 less than equals 0, and G2 equals again the same thing. So it's the G1 that you have to find out, the approximated G1. Okay. And the objective has nothing to do with it. Uh, so let me solve this problem. So first I'll write down, so G2 is already linear and all the options are anyway same. So now G1 xy is given as 4x square plus y square uh, minus 16 less than equals 0. So what you can do, you can approximate this as G1 xy approximated at that x1 y1 point plus grad of uh, G1 x1 y1 transpose, and then you will have x minus x1 y minus y1. So this is the first order approximation using the Taylor series expansion. Okay. So what you'll have here is that I'll write it as equals because already I've written that thing. Now it's 4 into 1 square, so it's 1 1. The point is 1 1. 1 square minus 16. Okay. Then what you have is the gradient. So gradient you have to find. So the gradient is grad of g1 x1 xy is 8x, and this is 2y. And at that point, it's 8 times 1, it's 2 times 1. So this is nothing but x minus 1, y minus 1. Okay, so the first one is 4 plus 5, 4 plus 1, 5 minus 16, so this is minus 11. And this is 8 times x minus 1 plus 2 times y minus 1. So this becomes 8x plus 2y, so it's minus 21. Okay, so this will be the correct answer. So 8x plus 2y minus 21. So option C is the correct answer here. Alright, so I think I'll just take this and answer this option C. Let me now move on to the third question. So it's a direct problem. So it's not a numerical, it's a theoretical. So I'll solve it. I'll write it down. Just I'll have some water and come back. Right, let me get started with the third problem. So, yeah, so let me write down the problem. So, the first is which of the following is or are true? So, there can be multiple answers as well. For a minimization problem in Zutendijk's method. Okay. So I think I've learned about Zutendijk's method in the context of feasible and decentralized interactions and usable directions. So this question is related to that. So I'll write down the uh, options. So it is related to the usable direction. So it says usable direction is both feasible or descent. Option B is usable direction is feasible but not descent. Option C is usable direction is descent but not feasible. Option D is none of this. So as you know that usable direction has to be both feasible and descent. So the option A is the correct answer, which is pretty straightforward. And the conditions you already know, I'm not writing it down. Probably that will follow the current problems. Anyway, let me get into the fourth one. So now I'm going into the exterior penalty method. So all these are theoretical questions anyway, so it's not much to explain. So exterior penalty method obtains a sequence of solutions by minimizing q c x equals f of x plus ck dx. Okay, so which of the following is or are true about the penalty parameter ck? Which of the following true about the penalty parameter? Okay, okay. So I'll write down the options. ck are negative and monotonically decreasing, which is not the case because we think that ck is at least like positive. So, or it can be c as well. Next one is ck are non-negative and monotonically increasing. So this is the correct answer. Option C is CKR negative. Again, this is not correct. And monotonically increasing. Increasing. Option D is CKR non-negative and monotonically decreasing. So this is also not correct. So answer will be option B. So this is again directly from the class. It's the correct answer. Okay, so 5, 6, 7, 8, all again are theoretical problems only, but there, I think some issues in one of the problems because of the option. Someone I think raised that issue already, but let me solve the fifth problem. Which of the following is or are true about the penalty function x of penalty exterior method? Okay, so the options are e of x tends to minus infinity as x tends to the optimal solution. B is p of x tending to 1 as x tends to the optimal solution. C is px tending to infinity as x tends to the optimal solution. That is not true because that's true uh, for the barrier method, right? And px tends to 0 as x tends to optimal solution. So option D is the correct one here. So option D is correct, and this is directly from the class. Again, self-explanatory. I think video lecture 54 does this one. Okay, let me solve the next three. So that will be straightforward. So I'll get started with that, but let me take a quick break and I'll come back because anyway I have time. I've already solved 5 problems. Okay, so let me do the sixth problem. So it's again on the exterior penalty method. So all these problems are related to this week's assignment. So exterior penalty method obtains a sequence of solutions xk by minimizing ucx equals f of x plus ck of x. So which of the following is so about the penalty, okay, penalty which is px about. So the options are, so penalty of this b is so this should be xk. C is we have xk plus 1. Now xk less than v of xk plus 1. Okay. So for this, I think this was discussed in the slides. So let me just quickly check in slides. I think uh, it will be in the 55th lecture of this course. Yeah. So the option pxk would be greater than equals to pxk plus 1. So that means option A should be correct. And then again, if you take the modulus, since these are non-negative penalties in general, because we put square terms, so even if you take the modulus, that should be correct. So A and C should be the correct ones. So let me see. That's the correct answer. Yeah, A and C would be the correct answers. This is true. And then again, since pxk greater than equals 0, pxk plus 1 greater than equals 0. So if you even if you take the modulus, this should be remaining as the same. But actually, there should have been a greater than equals to sign. But anyway, whatever is there in the option, let's go ahead with that. Anyway, there are a lot of typos in this option. So A and C are the correct ones. So now let me get into the seventh problem. So the seventh problem tells me exterior penalty method obtains a sequence of solutions xk by minimizing u of cx equals fx plus ck of x. Which of the following is not true about fx? True about fx. Okay. The options are fx k greater than fxk plus 1, which is not the correct one that we know. B is mod of fxk greater than mod of fxk plus 1. That's also not correct. Fxk is less than fxk plus 1, so that's correct. And then if have the modulus. So by similar logic, if you put your C value as very high, the functional values. So in general, what happens is that if you are dealing in the positive region, so yeah, that functional value will not have any dependency on the CK values. But anyway, if we are dealing with a function which is non-negative, then you can take modulus as such and get the answer. But again, I think the solution to this problem is still debatable. But anyway, option C is correct for sure, but option D they have also put as correct. But yeah, actually it depends on in which region you're working with. But anyway, I think for the sake of this problem, we can assume that you're dealing with positive region. Okay, so the answer will be C and D, but yeah, it's again the option D is kind of debatable. Yeah, problem 8 is the one where there was an issue because both option A and C are the same and it shouldn't have been that way. And again, here it's depending on the Q values. And okay, first I'll write down the problem. So problem 8 is exterior penalty method obtains a sequence of solutions scale by minimizing QCX equals fx plus ckpx. As before, then which of the following is not true? It's all not true. Okay, so the options are option A is q of xk greater than q of xk plus 1. Option B is if you take the modulus, option A is not correct. In fact, option B is also not correct because you can have some high penalty and depending on the C value, it might happen that you are dealing in the positive region. So option C should have been QXK less than QXK plus 1 because it has given us the same as option A. That's not the case. And probably someone raised this issue and that's why option C was also a correct answer. And option D is also correct if you again dealing with by the assumption that you're dealing with in the positive region. So yeah, I think I need not explain why the selections are true because these are already proved in the class. So options C and D are the correct ones. Then I'll start with ninth and 10th problem. So those are the numericals and a bit interesting in this assignment. So yeah, I'll start, but I'll just still wait to see if anyone joins because I have time. So by 4 I can complete this assignment and probably I'll just discuss briefly about assignment, the final assignment, assignment 12 briefly in 10 minutes and then just wrap things up or wait for people to join. Okay, so let me solve the ninth problem. Ninth and tenth both are similar, but it's a bit confusing because you choose the value of CK. So it tells you solve the following optimization problem. Then what you have is minimize fx equals x squared minus 10x subjected to gx equals x minus 3 less than equals 0 with the penalty function ex is max of 0 gx and square, right? Okay, so the options are x star equals 5, star equals 3, says fx star equals minus 21. Write down properly. Option D is fx star equals minus 25. Okay, so let me solve this. So what you have is fx equals square minus 10x. This is subjected to uh, gx equals x minus 3 less than or equals 0. And we know that the expression of x max of 0 gx equals to. Okay, now what you can write is you can write the q value. So you can write q equals ckx. So this is at suppose some kth iteration of x plus ck max of 0 comma x minus 3 whole square. Okay. Now what you have is qckx is x squared minus 10x if you don't violate the constraint. So if x is less than 3, or you have x squared minus 10x plus ck times x minus 3 whole square if x is greater than 3. Now, if x is less than equals 3, then if you just think about it as an unconstrained problem, or even you can think of it as a constrained problem, so that's not a problem. So if x is less than equals 3, so it might happen that if you just do the differentiation, so suppose I consider uh, so f prime x equals 2x minus 10, right, in that case. And if you set it to 0, then x equals 5, not true. So if x is greater than 3, or you could put it as greater than equals 3, then what you have is that q of ckx x square minus 10x. So this can be q prime of x, the previous one as well, so that's not a problem. Now you can have the first derivative. So this is 2x minus 10 plus ck times 2 times x minus 3. Now let's set this to 0, or you can take the second derivative as well. So that's 2 plus 2ck. Ck is positive, so this is greater than 0. So that means you are indeed minimizing this. And when you are minimizing this, what you can do, you can set q prime ckx to be 0. So that means your 2x minus 10 plus 2ckx minus 6ck equals 0. You can divide everything by 2, I think. X minus 5 plus ckx minus 3ck equals 0. Or you can take x as common, so that's 1 plus ck, 3ck plus 5, and your x becomes 3ck plus 5 divided by ck plus 1. Okay. Now, the thing is, this is the relation when you have this uh, first derivative set as 0. And now you have an additional condition that this has to be greater than equals 3. So if you check, this is indeed true. This is greater than equals 3. But again, in terms of this, you have to minimize your function, right? The value. So how would you choose the value of ck in this case? So that's the challenging part in this problem. So one way of doing it is that you start with some ck value and then uh, so that should be a non-negative value. So the initial you can have 0. So then x equals to 5 is your initial case. Then you can try and keep on increasing it. And after a certain point, it might happen that ck tends to infinity and then you don't do any improvements and so on, right? So ck equals, then you can put something like 2, then that becomes your next guess would be around, I think, 11 by 3. So you'll be moving closer to that uh, feasible region, right? So when ck tends to infinity, actually, this will be the solution. But the confusion here is that in the problem of the slides, it was written as ck tends to 0. But yeah, that's the thing. I think there was a mistake in the slide and the previous question. But yeah, I think it's better to ask the instructors about it because the options seem to be way off. So what you can do, you can divide it and have 5 by ck plus this is 1 by 1 plus ck. Now as ck tends to infinity, x tends to 3, that will be your minimum, and your fx tends to x square minus 10x, right? So that will be 3 square minus 10 into 3, which is minus 21. So therefore, what you have is x star equals 3 and fx star is minus 21. So that will be your correct answer. So option B and C are the correct answer here. So I hope this is clear, but again, there is some issue with the conventions. Uh, the one thing to notice here is that, oh, sorry. So we can have, let me check one thing. Yeah, so there could be another way of doing it since you are minimizing this. So the better way of doing it will be just so you have that relation, you can plug that back in, I think, in the original one. Uh, but you can express ck in terms of, so that will be the ck times x minus 3 equals 5 minus x. So ck is 5 minus x by x minus 3. So your q of now x becomes x square minus 10x plus 5 minus x. So this becomes x square minus 11x plus 5. Now you're trying to minimize this, right? But your assumption was that x is not equals to 3. So this is if x not equals to 3. But if x was equals to 3, then uh, so if x equals to 3, then you have qx or equals fx equals minus 21. So in this case, if you take the derivative, it becomes 2x minus 11. So again, uh, this is not true. This is violet. So this is the correct answer. So that's another way of thinking about the solution. Okay. Anyway, let me now solve the 10th problem, which is the final problem. And then I'll just probably wrap it up or go into the next assignment. Okay, so the 10th problem is again very similar. So let me write it down. Solve the following optimization problem. Okay, so this is minimization of fxy, which is you can write it as x plus y. This is subjected to g of xy equals x squared minus y minus 2 less than equals 0 with the penalty function g of xy equals max of 0 gxy whole square. Now the options are x star y star minus half minus 7 by 4. Option B is x star y star equals half 7 by 4. Option C is x star y star equals 0 0. Option D is x star y star equals 7 by 4 minus half. Okay, so let me solve this problem. Again, this is very similar. Let me write down the expression of the function fxy is x plus y. And then you have gxy is x squared minus y minus 2. This time equals 0. So what you have, okay, let me write down the pxy thing as well. X of 0, g of xy whole square. So what you can do, you can write q of ckx equals x plus y, which is fxy part, plus ck, then max of 0 x square minus y minus 2 whole square. Okay, so this is x plus y. So if there is a violation, then that would be right. So this ck square minus y minus 2 whole square. If you violate this, and if you don't violate it, it will be x plus y if the constraint is satisfied. Now you can take the gradient. So considering the first case, so this would be 1, then it will be 2ck square minus y minus 2 times 2x. And with respect to y, it will be 1 plus 2ck square minus y is 2 minus 1. So this is if x square minus y minus 2. Okay. Now, or it can be 1, 1 if square minus y minus 2 less than equals 0. So this is kind of not true because this is not 0. So let us consider this condition and try and set this to 0, right? So if you set this to 0, let me set this to 0. So I'm not going into the second order derivative because that would be a bit complicated, but anyway, we're minimizing it. So I think you can get it, what to do about it. Okay, so this should be, so my advice would be to write this down like this. So 2x times 2ck x square minus y minus 2 equals minus 1. Since you are setting it to 0, and for the other it's 2ck x square minus y minus 2 equals 1. Now you divide it, so you get 2x equals minus 1, and that gives you x equals minus half. Now you replace it to any of the equation to get the value of y. Okay, so let me do it in this second one. 2ck, this should be 1 by 4 minus 1 minus 2 minus 1 equals 0. So it's 2ck times 1 by 4. Okay, so this should be 1 by 2ck, and y is minus 7 by 4 minus 1 by 2ck, and x is minus half. So what you can now do, so the constraint was x square minus y minus 2 was equals 0. Okay, so that's 1/4 minus y minus 2 less than equals 0. So y is greater than or equals minus 7 by 4. Now as ck tends to infinity, okay, hi Paranidharan, I was solving the week 11 assignment problem, so I was almost done. I'm just solving the 10th problem. If you have any doubt related to the week 11 assignment, you can ask. This should be tending to minus 7 by 4. This is x star y star as minus half minus 7 by 4. And this is the correct answer. So option A is the one which is correct. So option A is correct, and that's all about the week 11 assignment. Okay. Okay. Do you have any doubt? Otherwise, I'll start with similar problems that you'll find in week 12 assignment. Let me open week 12 assignment. Okay, seems like he didn't have any question. He just joined to check or something. I don't know. Anyway, I'll just wait for a few more minutes and then I'll get started with week 12 content. Okay, so let me start with week 12 content. I'll just briefly talk about this problem. So it talks about this interior method, barrier function method. So the first one is directly from the video, the lecture. The second one is again talks about the penalty parameter. First one talks about the bx value, which is the penalty term as such. So again, you have to think about it. How do you approach this problem? So that's fine. So one and two both are like that. So let me solve the third problem, right? The interior barrier function method, a similar problem. So suppose like given as min of fx1 x2, say 4x1 square plus 7x2, subjected to say x1 plus x2 greater than equals 3 and x1 x2 then greater than equals 0. So solve by interior barrier function method. Okay, so let me check. So here, what you can do, you can have q of x comma ck as fx minus ck by 1 by gx. So what you can write here is that it should be 4x1 square plus 7x2. Uh, what you can do, can convert it into minus x1 minus x2 less than equals minus 3, or minus x1 minus x2 plus 3 less than equals 0. So this is minus ck by minus x1 minus x2 plus 3, or you can write it as 4x1 square plus 7x2 plus ck by x1 plus x2 minus 3. Now you can take, just like the other method that we have discussed today, you can take the gradient, and it will be 8x1. Then it will be minus ck by x1 plus x2 minus 3 whole square times 1. And the next one will be 7 minus ck by x1 plus x2 minus 3 whole square. So this is uh, so if the constraint is violated, if x1 plus x2 less than equals 3, right? Okay, so now for the other one, uh, we couldn't have set it to 0, so that's the issue that we would have had. But anyway, now a better way of doing it is to again, so 8x1 by 7 equals 1. If you consider x1 plus x2 not equals to that thing, right? So x1 plus x2 minus 3 not equals to 0. So that you have to consider for here from here, and that will give you 8x1 equals 7, and x1 is 7 by 8. Okay, so I think I'm not wrong here. It's fine. And then you have to find the value of x2. So that you can do by having, so suppose ck by 7 by 8 plus x2 minus 3 square equals 7. Or you can write ck, uh, that will be x2 minus 17 by 8 whole square equals 7, or x2 minus 17 by 8 whole square equals ck by 7. So once ck tends to 0, ck tending to 0, uh, 0 gives you x2 tending to 17 by 8. Okay, so that's about it, I think. Uh, yeah, so this is the answer. X1 star equals 7 by 8, and x2 star equals 17 by 8. So you can solve this problem similarly. So that's no problem. let's get into the fourth one. So it again asks you to solve this similar problem using interior burial function method. So it's the method is again same, so I'm not going to solve this. So 4 is similar to 3. Fifth one is an interesting problem, fifth and sixth. So suppose I give you maximize f of x1, x2, x3, x4 as x1, x2, x3, x4. And I also give you x1 plus x2 plus x3 plus x4 equals 60. Then I can ask you to solve this. So 5 and 6 are related to this. So what you can do, you can have some variables like s1 equals x1, s2 equals x1 plus x2, s3 equals, I think I've seen this technique in the class, and s4 equals x1 plus x2 plus x3 plus x4. This is uh, s4 minus x4. This is s3 minus x3. This is s2 minus x2. Right. So what you can do, you can have the first level. So that's f1 s1 equals x1 minus s2 minus x2. Then what you can do, f2s2 is suppose max of this is over x2 and this is x2 times x1, so I can put it as like this. So this is max over x2, which is x2 minus s2 minus x2, and you can take the derivative. So this should be s2 minus 2 of x2 equals 0. So that means your x2 star is s2 by 2. Okay, so now you can write f3 s3 equals max over x3 x3 times f2 s2, and this should be the optimal one, right? So plug this back in and that will give you s2 by 2 minus s2 minus s2. So this is s2 squared by 4. Okay, so once you put that in, so that will be x3 times s2 squared by 4. And again, s2 can be expressed in terms of x3 minus x3. S3 minus x3 so square by 4. Again, you can take the derivative, set it to 0, and this will be a bit complicated, but you can find it out. Should be okay. Let me expand this 2x3 is 3 minus x3 square. This should be minus. This should be plus. This should be s2 square plus x3 square. That should be now. How can do it? One of the ways of doing it could be you have to find x3, right? So it can be 1 by root 3, not 1 by root 3, it should be root 3 x3 whole square minus 2 root 3 x3 divided by 2 by root 3 x3 plus it should be 4 by 3 s3 square equals to 1/3 s3 square. So it's root 3 x3 minus 2 by root 3 s3 whole square. It's 1 by root 3 s3 square. So let me take the one of the roots, like the positive side of it, and we'll get this. So root 3 x3 equals uh, okay. I've done some mistake. Let me erase everything. Okay, 2 is 3 minus is 3, okay. All right, let me have it this way. Okay, now let me do it this way. Yeah, earlier one was also correct, but this is an easier way of doing it. Take this as common. X3 minus S3. So this becomes x3 equals s3 or x3 equals s3 by 3. So what happens when x3 equals s3? That means s2 becomes 0 and the whole thing becomes 0. So that's not true. So this part is not true. Okay, so now your f3 s3 was x3, which is x3 times s3 minus x3, so that's 2 s3 by 3, this whole square divided by 4. Okay, 4s3 squared. So this is s3 cubed divided by 27. Finally, what you have is f4s4, which is max of x4. This is s3 cubed divided by 27. And here also you can have the replacement x4. This is s4 x4 cubed divided by 27. Now set this to 0, its derivative, and again this will be a bit complicated. So this should be x4. So this is with respect to x4. So let me immediately remove that s4 minus x4 thing. X4 plus, yeah, there was an easier way of doing it also, but anyway, s4 is 4x4, so x4 star is this. So this is the correct one. And now what you have from the problem is that your x4 star s4 is, good news is that you know s4, so this is 60, and you have expressed this in terms of that, so this becomes 15. So once you know x4, you can know x3. S4 minus x4, so this is what sorry, done a mistake. So once you know x4, what you have to do, s4 minus x4 is s3. S3, okay, I think that needs to be your right. I hope everything that I've written is not lost. Okay, so yeah, you did have it. Fortunately, nothing is lost. Okay, so the first problem I was doing, and okay, S3 is uh, 16 minus 15 is 45. S2 is okay, so once you get S3, then you can get X3, which is S3 by 3. It's 15. S2 is again S3 minus X3, so that's 30. From that you can get X2, which is 30 by 2, 15. Then you can get S1, which is equals X1, which is 30 minus 15, 15. So the answer will be X1 star, X2 star, 4 star, all are 15s, and F star. So let's do, so this will be 15 to the power 4. Okay, so that's fine. Uh, so seventh problem is on multi-objective decision making and so Pareto optimal solutions and so on. So 7 or 8 are directly from lecture video. Ninth is on Pareto optimal, so multi-objective optimization problem. So actually I'll solve this ninth and 10th problem. If I do it now similar, I think you'll get the answer, but don't want to do it. 9 and 10. So it's on parent optimal solutions. So next week I'll solve it. So follow the lecture content. Okay, so I have some 20 minutes left, but since no one has joined, I'll just wait for 20 more minutes and I'll wrap up the session because I don't have anything else to discuss for today as I've already solved some 15 to 20 problems. Okay, Okay, so it's just 2 minutes remaining before 5 p.m. Since no one has joined and I've solved all the assignment 11 problems and discussed similar problems to assignment 12, I'll close the session for this week, and next week will be the last class where I'll be solving the assignment 12 solutions. Okay, see you all next week. Thank you.